Alright, the purpose of this video is to show you how to write the formulas of ionic compounds. So there's basically three different categories. You have what I'll call regular ionic compounds. They're just made up of two individual atoms. There's no tricks, there's no special things about it. We learned two different ways to do this back in chapter 7. The first is magnesium sulfide. What you do is you draw the symbol of magnesium and the symbol of sulfur, and you can either put the valence electrons on the atoms like we've been taught to do. Magnesium has 2 and sulfur has 6, and then you can do the work to figure out that magnesium will give its 2 electrons to sulfur. Sulfur needs 2, magnesium gives 2. Your other option is to do the charges. That Mg has a charge of 2+. You know this because it's a metal and it needs to get rid of 2 valence electrons because metals lose electrons. And sulfur has a charge of -2. It's a nonmetal, they gain. It has 2 open spaces, it has 6 electrons, needs 2 more to get to 8, so it's going to be -2. They have to add up to equal 0. So if I have a +2 and a -2, then they add up to equal 0. So either way I choose to do this, my formula ends up being MgS. Potassium phosphide is another example. Potassium is K, phosphorus is P. Potassium has 1 valence electron and phosphorus has 5. That means phosphorus needs 3 more electrons to get to 8. But potassium can only give 1. So if it gives 1, I still need 2 more electrons. So that's going to take 2 more potassiums to make phosphorus have 8 valence electrons. If I look at it in terms of charge, potassium is a +1. It's a metal, it has 1 valence electron and wants to lose it. Phosphorus is going to be -3 because it needs to gain 3 electrons to get to 8. If I do that, I can either crisscross the charges and put the 3 down here with the K and the 1 with the potassium, or I can figure that it's going to take 2 more potassiums in order to add up to +3 to cancel out the -3. Either way, I end up with K3P. We also did transition elements. And the thing about transition elements, if you remember, is that on the periodic table, they are in the defilling block. And we don't know their exact number of valence electrons unless somebody gives us some information. And that comes in the form of the Roman numeral. I have the Roman numerals down here at the bottom. You can pause here if you want to write them down, but you need to know at least how to do 1 through 7. If I have iron 3, what that's telling me is that I have iron that has 3 valence electrons. And so I'm going to write Fe with 3 dots, or I'm going to write Fe plus 3. Oxygen has 6 dots, or oxygen has a charge of -2. Oxygen is going to take 2 of those electrons, but after it takes 2, there's no more spaces. So I'm going to have to add another oxygen in order to take this extra electron, but then I run out of irons to give dots. So I'm going to have to add another iron. That makes the oxygen happy, but now I'm uneven with the irons. So I basically am going to have to go back and forth in order to get the correct number of dots here, and I put 2 dots there. I need 3 on the iron. And so both of these will go over here to my newest added oxygen. Now I have all of my dots from the irons going to the oxygens. If I do it with charge, then I can crisscross the charges. The 2 will go here, the 3 will go there, and I end up with a formula of Fe2O3. I still have the same thing using the dots. Copper 2 sulfide. Copper 2 has 2 dots. It has a charge of +2. Sulfur has 6 dots. Sulfur also has a charge of -2. Well, 1 electron, 2 electrons. This one's done. Same thing with the charges. +2 and -2 add up to equal 0. So this one's easier. The end formula is CuS. Polyatomic ions is the newest thing. A polyatomic ion is simply many atoms with a charge. So I put a couple of tips for you down at the bottom. One way to know that you have a polyatomic ion is that it always ends in ate or ite. So if I look up here, I see carbonate. That tells me I'm not dealing with just a plain old atom, because all of these other ones have ended in ide. Sulfide, phosphide, oxide, sulfide. So I'm going to start with the sodium, and it's exactly what I've been doing. Sodium has a charge of +1. Well, carbonate, I've got it memorized, but you guys don't. So you're going to use your lovely little periodic table here, your sheet, your reference table, has a polyatomic ion table on it. And if I look for carbonate, I'm going to find it down here towards the bottom. It's CO3 -2. What that -2 means is that it needs to gain 2 electrons. Well, every sodium has 1 to give, so the only way to make this work is if I have 2 sodiums. The 2 sodiums will give up electrons. That'll give up a total of 2 electrons. This will take on the 2. So my formula for this is going to be Na2CO3. On the example below this, there's a little bit of a difference with it. Magnesium nitrite. Okay, again, I see the ending in ite. Ite tells me it's going to be a polyatomic ion. Magnesium is just a plain old element. It's +2. It has 2 valence electrons to give away. It'll become a +2 charge. Nitrite. Okay, using your periodic table here, if you go find nitrite, you'll see it right there. Nitrite is NO2 -1. That means every nitrite can take on 1 extra electron. So this one can go right there, but I'm left over with another one. So I'm going to have to put another nitrite here to take that other electron, which means that my formula is going to be MgNO2. Now I need to put a 2 there. I need to show that I have 2 of that whole group. But if I do it like this, it looks like 22 oxygens. So whenever I have more than 1 polyatomic ion, I have to put parentheses around it. And I've put that note down here at the bottom, that you must put parentheses around polyatomic ion if it's more than 1. It's not an option. Notice on my example above, I did not put parentheses around it if there was just 1. You do not have the option to do so. You do not put it if there's 1, and you must put it if there's more than 1. In my next video, I'll be explaining how to turn these into the names that were on here to begin with.